program initially conceived for the purpose of pioneering liquid hydrogen technology, originally called for 6 research and development flight vehicles. A new letter contract issued by the NASA Lewis Research Center in January 1963 greatly expanded all phases of production and testing.
I am Ronald Rovinger, NASA Lewis Assistant Manager of the Centaur project here at General Dynamics Astronautics. The present Centaur contract, definitized in May of this year, calls for 15 flight vehicles, including the F-1 vehicle launched in 1962. 8 R&D flights supported by an extensive ground test program and 7 operational Atlas Centaur vehicles, each assigned the task of injecting a surveyor spacecraft into a translunar trajectory. There will be 3 more experimental flights before our first attempt to soft land a surveyor spacecraft on the moon. In the R&D phase, we are progressively adding operational hardware. As we review the highlight activities of the first 6 months of 1964, I will point out the configuration of each vehicle and show the progress made toward operational status. The basic vehicle configuration and flight test objectives for AC-2 and AC-3 were essentially identical. The major difference was in the nose fairing and in the insulation panels. The primary function of the fairing and panels is to protect the vehicle and spacecraft from aerodynamic loads and air friction heating during ascent through the atmosphere. A unique feature of the Centaur design is to jettison the panels and fairing when the vehicle is safely beyond atmospheric effects. Jettison improves Centaur performance by relieving the vehicle of nearly 3,000 pounds of excess weight. We did not jettison the short R&D nose fairing or the heavy insulation panels on AC-2. Ground testing of their separation system had not been completed. They were bolted securely to the vehicle. AC-3 flew the long surveyor jettisonable nose fairing and the lighter weight jettisonable insulation panels. Both of these items required extensive ground testing before they were ready for flight.
Insulation panel trajectories were studied under simulated flight acceleration rates to ensure that the panels would jettison properly and not endanger the vehicles. The next series of tests were to demonstrate that the panels would unlatch at liquid hydrogen temperatures. All gases and liquids except helium freeze solid at minus 423 degrees Fahrenheit. Panel seals and helium purge between the panel and tank wall were designed to prevent ice from forming and freezing the panels to the tank skin. The first 4 unlatch tests were unsuccessful. The smooth panel froze to the tank wall. This panel is the only one that does not have a tunnel. It thus has a much larger surface area in contact with the tank and less spring action when the hoop tension is released at panel jettison. The immediate solution was to replace the smooth panel with one having a tunnel, improve the seals, and increase the helium purge. The 3 succeeding tests demonstrated we had solved the freeze problem. In order to satisfy the urgent need to correct the problem, on the AC-3 flight vehicle, a tunnel panel allocated to AC-4 was modified for shipment to Cape Kennedy. Modification tasks involved sealing openings, changing instrumentation wiring, and exchanging the bolt-on angles. Astronautics began nose fairing jettison tests in March. Objectives were to evaluate the reliability of the jettison system, determine that the fairings will clear the spacecraft, and demonstrate that their trajectories are such that they will not collide with Centaur or Atlas. 3 successful jettison tests satisfied these requirements. However, as a result of the freeze problem encountered during the panel tests, a decision was made to run 2 additional tests at liquid hydrogen temperatures. The successful tests simulated an actual countdown, a 2-hour hold with propellants tanked, plus flight time to jettison. The additional weight of the surveyor nose fairing required that the structural maximum Q and maximum G tests be rerun in support of AC3. Certain phases of the tests also supported AC4 and AC5. Maximum limit loads applied during the tests were over 116 tons. Electric heater blankets simulated aerodynamic heating of 500 degrees Fahrenheit. The tests verified the structural integrity of vehicles AC3 through 5. Flight vehicle for AC3 passed final acceptance tests 22 January and was airlifted to Cape Kennedy 11 February. Following the Atlas Centaur mate, there were 84 major pre-flight tests. The most extensive of these was a full-dress launch rehearsal with both Atlas and Centaur tanked with propellants. The vehicles were then restored to a standby condition, awaiting completion of the insulation panel test constraints. The final panel fix on AC3 required careful fitting of all panels, including the modified tunnel panel. The seals were improved in all panel joints. Ground helium purge flow rate was increased and in-flight helium purge installed.
I'm Walt Hicks, Chief of Centaur Test Integration at General Dynamics Astronautics. We assigned Atlas Centaur 3 6 primary and 11 secondary flight test objectives. All flight test objectives were satisfied, with the exception of full duration burn, successfully demonstrated on AC2. The first objective was to obtain data on the launch-on-schedule capability. Complex 36 launched AC3 within 4 minutes of the scheduled liftoff time. This was well within the limits of a surveyor launch window. Second, the successful separation of the insulation panels and nose fairing was an important first. All instrumentation indicated that the panels and fairing withstood the loads encountered during ascent, provided the necessary thermal protection, and jettisoned properly at the exact pre-programmed time. Atlas and Centaur separated at T plus 232 seconds. There were no indications of system malfunction or mechanical interference as the two stages parted. All events, up to and including Centaur main engine ignition, were nominal. 5 seconds after main engine ignition, the vehicle lost gimbal control of the C2 engine due to a hydraulic failure. This in turn caused the vehicle to roll. Both engines continued to burn for 257 seconds. At this time, increased roll forced propellants against the oxidizer tank, uncovering the oxygen pump inlet. Oxygen starvation shut the engines down 120 seconds short of the full duration burn. However, after main engine shutdown, the attitude control system stabilized the vehicle, and a planned post-powered flight experiment involving the boost pumps was conducted. Objective 5, verify structural integrity throughout all phases of powered flight. The vehicle rolled about its center of gravity at the rate of approximately 1 revolution per second. This imposed stresses on the vehicle far greater than nominal flight conditions. Centaur maintained structural integrity throughout this extreme maneuver. Guidance on AC3 flew open loop for system evaluation. We do know the system operated throughout the flight, including the period of uncontrolled vehicle roll. Analysis at this time is incomplete. The hydraulic failure at this moment is difficult to account for in that the system has a long history of successful operation. It has never failed on the engine in numerous tests at all sites: Edwards Rocket Site, Sycamore Static Test, Lewis Space Chamber, Pratt & Whitney, and the Eastern Test Range. The fact remains the C-2 engine lost hydraulic pressure during the flight. We have excellent telemetry data that is helping us isolate the possible causes of the malfunction. The Lewis Research Center and General Dynamics Astronautics are thoroughly investigating all potential failure modes. The problem will be solved and immediate action taken.
The next flight vehicle, AC-4, reflects a number of advancements in support of the final operational design. The primary flight test objective will be to demonstrate for the first time Centaur guidance closed loop. In addition, the vehicle has a surveyor mass model, a spacecraft mounting adapter, and a newly designed coast phase ullage engine. AC-4 is slated for a two-burn experiment as one of its flight test objectives. Between the first and second burns, the vehicle coasts for approximately 25 minutes.
The new ullage engine installed on the AC-4 aft bulkhead is designed to prevent the propellants from floating free in the tanks during the coast phase period. The engine is a modified attitude control cluster uprated to 4 pounds total thrust. The two hydrogen peroxide thrusters will fire continuously during coast phase, maintaining the propellants in the aft end of the tanks ready for the second burn. AC-4 will fly a mass model simulating the Surveyor spacecraft weight and center of gravity. The 2,100-pound model mounts on an operational Surveyor adapter fitted with a payload separation and jettison system. AC-4 will be the first vehicle to fly with the Centaur guidance system closed loop. 10 seconds after booster engine cutoff, the guidance system will control both Atlas and Centaur for the remainder of the flight. The heavy-walled T-7 test vehicle, previously used at Edwards Rocket Site, supported AC-4 propulsion tests at Sycamore Canyon Test Site S4. Gimbal tests demonstrated the structural integrity of the propellant supply ducts and the airborne portions of the helium ground chill-down system. 2 cold flows verified that the propulsion and related systems were ready for hot firing. By 30 June, Sycamore had completed 3 of the 5 required hot firings. AC-4 passed final acceptance tests in June. The vehicle is scheduled for delivery to the Eastern Test Range in July.
AC-5 will fly a lightweight slosh baffle, an advanced propellant utilization system, and a Surveyor dynamic model.
The first of the advanced propellant utilization systems for Centaur was installed in AC-5 on 10 April. The system is designed to achieve payload gains by controlling the mixture ratio of liquid oxygen and liquid hydrogen so that no more than 150 pounds of one propellant remains at the depletion of the other. AC-5 will be the first vehicle to fly a dynamic model of the Surveyor spacecraft and inject it into a simulated lunar transfer orbit. Hughes Aircraft, contractor for Surveyor, supplied the model. Astronautics is providing the telemetry and post-flight analysis.
The AC-6 configuration represents the present operational design for one-burn missions. Centaur designers achieved extensive weight reductions on the tank and in the interstage adapter. They reduced skin gauges, chem-milled the forward bulkhead, lightened the thrust barrel, eliminated the wetting ring, and moved the intermediate bulkhead back 4 inches. Moving the bulkhead aft reduced the ullage space in the liquid oxygen tank, eliminating the need for a slosh baffle. At the same time, it increased the fuel capacity in the liquid hydrogen tank by 26 cubic feet.
Redesigns lightened the AC-6 adapter 433 pounds. Chem etching the heavy aluminum skins and removing half of the internal rings accounted for most of the weight reduction. The AC-6 tank moved to Edwards Rocket Site for cryo test on 1 April. Conversion of Stand 1-1 from propulsion to cryogenic testing began in late 1963 and was completed on schedule 3 April 1964. The tests demonstrated the structural integrity of the tank, determined the vacuum characteristics of the intermediate bulkhead, and evaluated the propellant utilization system. Following successful completion of production cryo testing, the tank returned to San Diego for final assembly on 7 May. AC-7, the first operational Centaur, is scheduled to place surveyor spacecraft SC-1 on the moon in 1965. As of 30 June, the vehicle tank for AC-8 was 95% complete. This vehicle will serve as a continuation of the AC-4 two-burn mission study. The vehicle tank for AC-9 entered the major weld fixture on 17 June. Most of the AC-10 tank subassemblies are complete and ready for major weld. AC-11 bulkhead buildup is progressing on schedule. Concurrent with the accelerated activity in vehicle production, there are a number of extensive test programs contributing to Atlas Centaur development. Separation tests in the Lewis Space Power Chamber revealed an Atlas retro rocket problem. Several rocket misfires resulted in an intensive investigation. Examination of the rockets disclosed that the igniters fired but failed to ignite the propellant. The problem has since been corrected. Testing continues at the Lewis Plumbrook Stand E1. The purpose is to ascertain the dynamic characteristics of the Atlas Centaur surveyor vehicles under a wide variety of flight conditions. The Lewis Research Center is preparing to test a complete flight-type Centaur vehicle in a space chamber. This will be the first time that the total vehicle will be subjected to simulated flights in an environment closely approximating space conditions. Holloman Air Force Base in New Mexico has many facilities for advanced space research studies. Included among these is the longest precision rocket sled track in the world. Their staff of Air Force engineers and civilian specialists have run a series of 14 Centaur guidance evaluation tests on the 7-mile track. The NASA Lewis Research Center is primarily interested in system performance under linear G loading and simulated flight vibration levels. The guidance packages are mounted in the sled forebody. The liquid propellant rocket develops 105,000 pounds of thrust, accelerating the sled to over 800 miles per hour in less than 8 seconds. The system and early generation guidance set not only performed well under conditions more severe than it would experience in flight, but also displayed functional accuracies in excess of those originally predicted. The sled test program began 6 February. The 14th and final test was run 11 June. In San Diego, Combined Systems Test Stand construction began 18 February. Activation is slated for November. The facility will simulate an ETR launch with the combined Atlas Centaur Surveyor spacecraft in flight configuration. Any problems discovered may then be corrected at the factory and prevent time-consuming delays at the launch complex. The facility constitutes a vital launch on-time link.
The experimental flight of AC-3 achieved 16 of 17 assigned test objectives. Of the 536 telemetry measurements, 98% supplied valid data. The successful jettison of the insulation panels and nose fairing was a major achievement in liquid hydrogen technology. Centaur is progressing toward the first surveyor launch in the coming year.